In this lecture, we're going to talk about the speed limit on the sorting algorithms of the type that we've seen so far. Before we talk about that, let's do a quick review on the definition of an inversion, since we're going to talk a lot about it today. An inversion is a positioning of two elements in an array that we want to sort, which are out of order. And the mathematical definition is that if we have two array indexes, I and j, where I is less than j, it is the case that a sub j is less than a sub I. These two things are out of order. So we've already talked about that, and let's look at this array here that I've highlighted. How many inversions are there in this array of 6 elements? Well, if we look through and we look at the element 0, there is no inversion involving 0 because 0 is the least and everything after it is greater than it. So there's no inversion involving 0. If we look at 5, there's at least one inversion involving 5, which with its subsequent index, which has the value 3, and those are out of order. There's also, and that's highlighted by this marker right here. Okay, so that indicates, for this example, an inversion. But there's also an inversion down here between 5 and 2. Okay, 5 and 2 are also inverted. So those are two inversions involving 5. We already have talked about the inversion involving 3 and its predecessor. Are there any successive elements that involve 3 that are inversions? Well, yes, there's an inversion between 3 and 2, and so on. So if we count all of them, we've got one between 7 and 2, and then we've got one between 9 and 2 as well. So all told, we have 1, 2, 3, 4, 5 inversions in this array. Okay, so that's just review on the concept of an inversion. So what we're going to talk about today is how fast can a sorting algorithm of the type that we've looked at so far run. And what we're talking about is a lower bound. This is a big omega bound. So we're not talking about big O, we're talking about what's the fastest lower bound for how quickly an algorithm can run. And we'll say it can't run any faster than this. And that it requires at least this much time. That's what big omega says. And for today's discussion, not for subsequent discussions, but for today's discussion, we're going to have 3 restrictions. And the first one is what we've been talking about so far. It's one of our fundamental assumptions that we're going to only deal with comparison-based sorting algorithms. The second assumption is that we're going to only compare and swap adjacent elements. So we might have inversions, as we saw up here, we might have inversions that are far apart from each other, like between 5 and 2, but we're not talking about algorithms that compare those or swap those at that long range. We're talking about algorithms that only deal with inversions between adjacent items and swapping those items, okay? And so one way to say that is we're only looking at things that look at some index a sub I and its successor a sub I plus 1, or its predecessor. The two of the algorithms that we've looked at so far, bubble sort and insertion sort, are these types of algorithms. They compare only adjacent items and they swap only adjacent items. So these are the types of algorithms that we're talking about. And the third assumption that we're making is a simple one, is that we're sorting arrays of unique numbers. There are no duplicates, and that's a minor point, but we'll just state that out up front, okay? Now, if we have inversions, we know that if an array is inverted, or has some inversions in it, rather, if there's some inversion in an array, then we know that it's not in sorted order, because an inversion is something being out of sorted order. So the first, I want to take this discussion, this proof, in 3 steps. The first step is how quickly can we remove inversions? And suppose we have an array with some inversions like the one that we were just talking about. If we were to do the following, if we compare and swap one inversion between adjacent items right next to each other, how many inversions does that remove? Okay, so think about this for a second. I'm going to pause and let you think. If we identify an inversion between 2 adjacent items, and we remove that inversion by swapping those two items. How many total inversions does that remove from the entire array? And the answer is just 1, right? If we say take 5 and 3, if we were to swap 5 and 3, then 3 and 5 would be in that order, and there would no longer be an inversion here, right? There would not be an inversion between 3 and 5. And so we've removed that one inversion. Any other inversion that exists between 3 and anything before or after it, and 5 and anything before or after it, except for the 3 and the 5 themselves, does not get removed because we're only swapping these two adjacent items. So any inversions that were longer range than that are not removed by swapping two adjacent items. So that's the key insight here, is if we compare and swap one pair of adjacent items that are inverted, we remove that one inversion and no others. Okay, so that tells us something. If we want to sort an array that has inversions, that's not sorted, we need to be able to remove all the inversions to get it into sorted order. And so the number of inversions is going to correspond to the number of operations we expect to have to do when sorting this array. So if we can identify how many inversions there are in an array, we can identify how many inversions we have to remove. And since each comparison and each swap that we do removes one inversion when we're looking only at adjacent items, then if we can identify the number of inversions there are, that corresponds to the number of essentially swaps that we need to do. And those number of swaps is determined by however many comparisons that we do. We can only swap two items and uninvert them if we know that they're inverted, and we can only determine that they're inverted if we do a comparison. And remember that we're trying to count the number of comparisons, the number of less than operations. And so that's ultimately what we want, is how many comparisons do we do? Well, that corresponds directly to the number of inversions that we're going to see in the array. So step one, what we have identified is we can, with these types of algorithms, remove one inversion per comparison and swap if we find it, because we're looking at adjacent items, and therefore the number of inversions is exactly the number of comparisons and swaps that we will need to do in these types of algorithms. So if we can identify the number of inversions, then we know the number of comparisons and we know the running time of the algorithm. So that's step one. Step two, how many inversions could there be in an array? Well, let's talk about this from a sort of basic perspective. What's the minimum number of inversions in an array? Well, of course, it's 0. If an array is sorted, there are no inversions in that array. The number of inversions is 0. And what's the maximum number of inversions that we could have? Well, the maximum number is that the array is completely out of order. So if we had an array that looked like this, 5, 4, 3, 2, 1, right? What do we find? We find that 5 is inverted with respect to all 4 that succeed it, right? And not including what comes before it, not including, not double counting things. If we look at 4 is inverted with respect to everything that comes after it. In other words, there are 3 inversions that involve 4 and its subsequent elements. 3 is inverted with all of its subsequent elements. 2 is inverted with its subsequent element. So the maximum number of inversions in general is going to be n times n minus 1 divided by 2. Okay, and we know this identity because we've seen this identity. This is the sum for I equals 1 up to n, right? It's actually up to n minus 1 of I. Okay, and we know this identity. And that's equal to n times n minus 1 over 2. Okay, so the minimum number of inversions is 0. And if the array has no inversions, it's sorted. Therefore, we have essentially no inversions. We have no inversions to remove, so the running time could be fast. The maximum number of inversions is n times n minus 1 over 2. And in that case, we have to remove all those inversions. And that means that the running time is going to be on the order of n squared comparisons, because we have to make a comparison for each of those inversion swaps. But not all arrays are completely sorted, and not all arrays are, in the worst case, reverse sorted. In fact, if it was reverse sorted, it's actually easy to put it in order. You just reverse everything. But let's consider sort of the in-between case. If you have just an array that has a certain number of inversions, what happens when you reverse it? So for example, here's the array that we were dealing with before, 0, 5, 3, 7, 9, 2. And here's its reverse, 2, 9, 7, 3, 5, 0. Notice that everything that was inverted in the forward direction is not inverted in the reverse direction. So if we take an array and we reverse it, everything that was inverted becomes uninverted, and everything that was uninverted before becomes inverted when we reverse it. Okay? So that's a key insight too. If we have an array that has k inversions, well, k could be anywhere from 0 to n times n minus 1 over 2. How many inversions are in its reverse? Well, do you know? If the maximum number is n times n minus 1 over 2, then the reverse sorted array, or the reverse ordered array, I should say, has n times n minus 1 divided by 2 minus k inversions. Okay? So, we have an array, we have its reverse. One has k inversions, one has n times n minus 1 over 2 minus k inversions, because everything that was inverted becomes non-inverted, and everything that was not inverted becomes inverted. So then here's a question. How many inversions are there between an array and its reverse if you add those together? Well, if we have k and n times n minus 1 over 2 minus k, then that's just n times n minus 1 over 2 minus k plus k equals n times n minus 1 over 2. Okay? So if we pair up an array and its reverse, the total number of inversions between both of those arrays is always n times n minus 1 over 2. And that's getting us somewhere, but we don't have the full picture yet. Okay? What we need to do now is we need to talk about how many inversions do we expect to see in any array. Okay? That's step 3. How many inversions do we expect to see on average? And I always like to ask the question, well, what do you mean by average? How would you determine what an average looking array looks like? If you saw an array lying on the ground as you walked past, would you be able to tell what an average array looked like? Say that's an average array. Well, that's not an average array. Well, we don't know exactly what an average array is going to look like, but what we can do is we can calculate on average how many inversions an array just plucked out of thin air might have. So the average number of inversions is going to be an average of this quantity that we just talked about. Every array and its reverse have a sum of n times n minus 1 over 2 inversions. So what's the average number? The average number is half of that. So n times n minus 1 over 4. Why is this true? Well, because every array has a certain number of inversions. Its reverse has sort of the complement number of inversions, n times n minus 1 over 2 minus that number of inversions. And if you pair these all up, then what you get is per array an average of n times n minus 1 over 4. And this is on the order of omega n squared. Okay, so if we have on the order of omega n squared, so this is at least n squared inversions on average per array, then what does that imply? Well, the consequence of that is that any sorting algorithm of the type that we're talking about that compares and swaps only adjacent items has a speed limit of big omega of n squared. It has to remove on average, n-squared inversions. It can only remove one inversion at a time using one comparison and one swap at a time. And therefore, on average, it's going to require at least n-squared comparisons and swaps, which tells us something a little bit depressing, that algorithms such as bubble sort and insertion sort, which fit this model, they can't go any faster. We can't make them any faster without sort of completely redesigning the way the algorithms run, because both bubble sort and insertion sort have this property that they only compare and swap adjacent items, and therefore they only remove one inversion at a time. Interestingly, this is a lower bound, but this is an average case lower bound, and we have not done an average case analysis before. The reason it's an average case is because we know that this isn't the best case, which is a sorted array, and it's not the worst case, which is a completely unsorted array or a shuffled array. This is looking at all possible arrays. What do we expect the number of inversions to be? Okay, so it's statistically speaking, it's an average or an expectation. We haven't really done the math in detail to support this, but that's what it is. The last consequence that I'll point out is that in order to move on from this and to get a sorting algorithm which runs faster, we are likely to need to be able to remove more than one inversion at a time. So our limitation right now is comparing adjacent items and removing one inversion at a time. If we can remove more than one inversion with one comparison and one swap, for example, if we compared and swapped things that are far apart, maybe we can remove more inversions in one step than what we have been doing. Then maybe we have a chance of moving faster in our sorting algorithms. Okay. I will point, and in fact, that's where we're going. But I will point out that even though selection sort, which I've already told you, is a pretty terrible algorithm, even though selection sort does this, it compares things that are far apart and it swaps things that are far apart, it still has this terrible behavior where it's big omega of n-squared. So just the simple fact of comparing and swapping things that are far apart is not the only solution to this, to speeding up these algorithms. We have to have a better algorithm. Okay, so in future lectures, we're going to then start looking at faster algorithms which have these properties.